I just got back from the first flight of my new airplane. This is a design from the flight test forums. I will link it in the description. And it's cool because it's got a pusher prop, so it flies this way, the propeller pushes it. And it's got twin booms, so it has a normal tail. That means it's a 3-axis control system. It has ailerons. It has a single elevator in the center, and it's got the 2 rudders. So that gives you roll, pitch, and yaw, respectively, which should make it pretty fun to fly. I'm trying to use it as an FPV platform. So I've got my DJI FPV system up front. I've got a big open bay in the center for batteries. Here's the battery Velcro and a battery strap. Got an Omnibus F4 Pro flight computer in here. So this one has a current sensor. It's got the popular STM32 F405 microcontroller that basically all these F4 flight computers have. I got a little beeper on this one and a 20 amp ESC with a BEC. The motor is a little quadcopter motor. This one is a 2205 size and it's 2300 kV, so 2300 RPMs per volt of input. And then this has a TBS Crossfire long range receiver on it. So we got an XT60 battery hookup, and I designed this plane to balance with a lot of different batteries. That's why it has the huge battery bay. I'm trying to fly it with this 4S 3300 milliamp hour battery. So 60C might seem a little bit low. So this can discharge 60 times its current capacity per hour, essentially, per unit of time. So 60C discharge for this battery would mean 60 times 3.3 amps. So that's actually high enough for a fixed wing plane like this. It might not be high enough for a really big multi-copter, but for a fixed wing with a small motor, that's what I'm going for. I want long and kind of slow flight times with a good range. The plane flew kind of weirdly on the first flight. It was somewhat back heavy. So in the original design, I think the tail boom is longer. I've shortened it a little now. And you can see I've got these carbon fiber rods as the booms. The original design called for wooden dowels, but I'm using carbon to try to lighten it and stiffen it. So any flexibility in this tail section causes the flight to be wobbly. So as the flight computer corrects the attitude of the plane, if there's a little bit of slop or flex in this tail boom assembly, then you can get into some oscillations, and it looks like the plane is cycling up and down. So that did happen on the first flight. It felt back heavy and entered kind of a stall pattern. I had to kind of nose it forward and give it a lot of throttle. So I shortened the tail a little bit. I'm gonna try to move the battery even further forward. That should all move the center of gravity forward. And meanwhile, I tried to stiffen these booms. So with this plane, I'm trying something new. It's a little bit messy because it's a research plane. That's my excuse at least. So I've got these zip ties in little plastic grommets on here. The zip ties go through the foam core. And let's look at the bottom. So on the bottom of the wing, I haven't tucked the wires out of the way yet, but I got my servo extensions going to the tail. And then you can see that I had to repair the wing here because the plane crashed after its first flight. And when it crashed, the fuselage stayed sort of level with the ground, but the tail flared up away from the front of the wing. So to mitigate that tendency, I've got a new zip tie at the leading edge of the wing here, and I've extended this carbon spar forward, the carbon boom, and then I have 2 zip ties along the middle and the back of the carbon fiber rod. So these little 3D printed pieces of plastic are little cradles for the carbon, and my hope is that the zip tie going through the foam will be a lot stronger than just a big blob of glue on the surface. And glue doesn't really stick to this carbon rod very well, so I need to use some kind of mechanical fastener like this one. So with those improvements, I'm hoping the plane's gonna, one, withstand hard landings a little bit better, and also be more rigid in the air, so reduce some of that swaying motion. I've got 9-gram servos here controlling the ailerons, and the original design called for all 4 servos to be along the wing spar. So you put 2 more servos up, 1 on each wing, and they would have control arms that reach all the way to the tail. And the benefit of bringing the servos up to the front of the airplane is that the center of gravity comes forward. And usually you're always trying to move the center of gravity to the nose. Planes are often tail heavy, and you might need to put a extra ballast in the front or an even bigger battery or shift everything forward. So you want to minimize the weight of the tail. I figured it would be much easier to get a solid mechanical link if the servos were in the back of like near the tail. So they have much shorter control arms. And so far that seems to work. It is a little bit tail heavy, so even if I get it to balance, the mass that's here out on the tail is going to contribute to a higher moment of inertia. So the further away you put the mass from the center of the aircraft, the center of gravity, the more difficult it'll be to turn the airplane, even if it's balanced. So keep in mind when you're moving mass out to the edge, like to the wingtips, to the tail, you're going to increase the moment of inertia, which is the difficulty of rotating the plane essentially. And it actually increases as the distance squared. So every little bit you move back, a servo is going to have a pretty profound effect on the way the plane feels to fly. And this is going to be, I want this to be sort of an FPV cruiser, so I'm okay with a little bit more docile behavior. I noticed in flight that these tail pieces weren't staying very vertical, so I added these carbon V braces here. These are new. They're not very elegantly attached. They're sort of in a little puddle of glue. If I like the way it flies, then I'll probably print some little brackets to hold these more elegantly. I was kind of trying to keep the custom parts to a minimum, but now you can see they're all over the place. So we've got the 3D printed Spawn's control horn from Dan Sponholtz, who designs a lot of these planes for flight test, and then released as the drawings. Then you have like the control horn here. So these link the rudders together, this tie rod. Here's the servo that controls them. And then you got one for the elevator. So the 3D printer's been really handy for things like the control horns. And I'm thinking about using it for braces like this. But for now, these are just pieces of carbon that are glued in. And you can get carbon rods like this really cheaply. These are like 2 millimeter diameter. On the wing, you can see I also have just some music wire and another 3D printed control horn with the 9-gram servo. So these servos are just, make sure they're glued in really tightly. They're embedded so they don't wiggle. The overall architecture of this plane, backing up a little bit, it's a single wing that with a sort of flat front. So the wing is not swept back at all. So it's actually swept, it's just so that the front is completely flat. And that's supposed to improve its stall handling characteristics and potentially generate a little bit of lift from the wing vortices hitting the body of the plane. I just chose it because it's worked for me in the flight test Goblin, and I like that, the way it flew, so thought I'd try it again. This results in a really stiff wing, just having one piece, and the original design calls for a fuselage that slides sort of over the front of the wing and straddles it. So that would be like a mid-wing configuration. And for this FPV platform, I went with a low wing configuration. So it's actually a little bit less stable than a high wing, because we have the mass, the center of gravity is going to be somewhat above the wing. The nice thing though is that you can add this strike plate on the front so that in a grass landing, your camera's not down in the grass. You can also put the motor and propeller up off the ground. So I like the high wing basically for landing it. And so far, I think it flies okay. The center of mass problems and the flexibility were much more concerning than the position of the wing to me. With a flight computer, running iNav like this one is also going to have some artificial stabilization, which will help it fly better. So I mentioned that the plane crashed after its first flight. It actually did the full maiden flight fine. So it didn't fall out of the sky, but it did have some really weird oscillations and went into interstall. So I brought it down, and I thought the propeller might be on backwards, but it wasn't. It's a little bit noisy. I think that might be because of the 4S battery. I'm used to the sound of 3S. But ultimately, it ended up crashing, and the flight computer was playing the SOS beep pattern, which means it was in a failsafe mode. It didn't have any reception from the transmitter. And I thought, like my other recent plane build, that this one had failed because the ESC blew up, and that there might be something wrong with the voltage regulator. So I took it open today, preparing for the worst. I thought I was going to replace the ESC or BEC at least, or maybe even the flight computer. But it turned out that the receiver cable had just come unplugged. And this Omnibus F4 Pro has little ports that you can plug in. I don't even know what connector this is. This small connector that's like a GPS connector for your receiver. And this is just pulled out. So I've attached some hot glue to the connectors now. I guess that's common practice that I should have done originally. And that's going on my build checklist. One last thing I'd like to say about this plane before I fly it again. I had used Velcro, I thought I was being clever, to hold the flight computer mount in, to hold the camera to the load floor here. I will say I don't recommend Velcro for things like that. This flight computer needs to stay oriented in the same position with respect to the fuselage for the whole flight. So, because it's determining, based on its own orientation, how to control the plane. So, if the flight computer is wiggly, like it was on the Velcro, then if it shifts during flight, the whole plane is going to change its attitude to compensate. And that'll result in some really weird flight characteristics. So this is on Velcro. I didn't feel like ripping off the paper from the foam to get the Velcro off, but I've zip tied it down with a zip tie through the outside, so a little tacky. And I put a bead of hot glue on the top just to really lock it in place. So this makes it harder to work on if I have to get it out and solder on it, but you want this to be super rigid, so that's the trade. And I had mounted the camera, like I said, it's on a 3D printed bracket. Let me see if I can zoom down in here. So you can see that it's on a little A-frame to hold it in place, and the transmitter is right beside it. These things were Velcroed here, that's why there's Velcro on the load floor there, but the camera is so small that it just ends up wobbling around. Velcro doesn't have a very good, it has quite a bit of slop before you start to peel it apart. So these are glued down now, and I'm going to glue these in the future. The advantage of using these 3D printed brackets is that you can take the fasteners out and get these parts out. The camera is going to be a little bit hard to reach because of how it's tucked in beside the transmitter, but I'll worry about that when I have to take it out, and maybe I'll just break the glue. So this plane doesn't really have a name yet. I don't even remember what the original author called it. I think he just called it a single sheet twin boom design. So if you think of any names, let me know. But I'm going to be flying it again, see how it behaves. I'm hoping the forward center of gravity, a little bit of shorter tail, and the increased stiffness are going to dramatically improve the flight characteristics.